Hi AP Stat students, this is our last video of the year, which is super exciting, on inference tests for linear regression. So you're going to figure this all out pretty quickly. The scatter plot below shows the population distribution of all 222 eruptions from Old Faithful in 1 month. The duration is how long the eruption lasted, and the interval is the time since the previous eruption. Okay, so this would be 2 minutes since the previous eruption, and it only lasted 45 minutes. This means the least squares regression line is a population regression line, right? The line is based off of all 222 eruptions. It has a slope of 10.36 and a y-intercept of 33.97. So imagine that we take a SRS of 20 of these eruptions, right? We don't want to choose all 222 because that would take forever. So we only take a sample of 20. When we find the regression line of our sample, it is a sample or estimated regression line as opposed to the population regression line. You can probably see where we're going for this. So those blue dots, I know it's a little hard to see, but the blue dots are the sample out of the orange dots, which are the population. So this was a different sample of blue dots, and this was a different sample of 20. Notice how the y-intercept and the slope vary. There's your sampling variability, aka that's why this is a statistic. How do the slopes compare to each other and the slope of the population? Well, the population, remember, was 10.36. This one was very close. This one was about 3 below. This one was 1 below. Imagine we took 1,000 samples of n equals 20 from the population distribution and measured the slopes. The result would approximate a sampling distribution of the slopes. See what we're doing here? Remember, the population regression line is this. Okay, so this is a distribution of B, our slope. Sometimes we get slopes that are bigger, sometimes we get slopes that are smaller, and this is a simulated sampling distribution, so it's not perfect, but it's not bad at all. So we can describe the shape. Well, it's approximately normal, as we expect when we have a sampling distribution. The center is around, oh my god, 10.3, which is the slope. The spread, you can see that it starts at around 5 and ends at around 15.5. We use the sample regression line to make an inference. Okay, we can do a confidence interval or a hypothesis test. Those are both inferences about the population regression line. We will focus on using the slope of a sample regression line to estimate the test or test the slope of the population regression line. So the population is our mu of y as opposed to y hat, which comes from the sample. Alpha, right, all of our Greek symbols are telling us what's the population. A is our sample, alpha is our parameter, right, our population, and beta is our population slope, while B is our sample slope. So over with that Old Faithful, we should have said mu of alpha, but that's okay. So the conditions, there's a few more conditions. So this is our last acronym, but it's LINER. So linear, we need a linear relationship between x and y. We need independent, right? That one's the same. We need a normal sampling distribution. We need equal variance. I'll talk about that one. But this one is the standard deviation of y, call it sigma, is the same for all values of x. Okay, so the standard deviation needs to be the same. I'll show you what that looks like. And then random, we need to have a random sample or a randomized experiment. That's not new. So most of these conditions are checked using both the scatter plot and the residual plot. And I'll show you what that looks like in an example. Here's a little bit more on this stuff, right? We want to see that the pattern is roughly linear. So we're looking for curves in the residual plot, right? We want no pattern in our residual plot to satisfy this condition. We want to look at how the data were produced. We want random sampling, random assignment, and if the sampling is done without replacement, we want to check that the population is at least 10 times as large, right? That same 10% condition. which will be probably what we use most of the time. Normal, we make a stem plot histogram normal probability plot of the residuals. We want normal residuals, and then we check for skewness or other major departures from normality. Equal variance, again, I'll show you what this looks like, but we're going to look at the scatter plot of the residuals, and the amount of scatter should be roughly the same from smallest to largest. So what this means is no fanning in or out. Again, I will show you what that means. And then random, we already know that one. So with confidence intervals, we have the same sort of situation, and we want to think back to our old faithful data from last week. So imagine we took every possible sample of 20 eruptions and found the least squared regression line of each sample. Then we plotted the slope of the regression lines. We would have a sampling distribution of slopes, right? Talk about this, right? This is our population, so this really should be mu of y, not y hat, right? Because y hat's our predicted sample. So we have a normal shape. Here's a formula for spread. We have sigma over standard deviation of the x's, and then divided by n minus 1. Now, I don't think you will ever have to calculate this on your own, and then here we can create a t interval. We're using t because we have samples, right? We're not using proportions. It's similar to means instead of proportions. So we have our slope, our test statistic, right? This is our sample slope. And then we have our critical value, t star, and then we have the standard deviation of the statistic. Okay, here's another thing with the degrees of freedom though. Instead of being n minus 1, we're going to be n minus 2. You can remember that because we're using two variable statistics. Fidgeting and other non-exercise activity, right, we did this in chapter 3, explains why some people may spontaneously increase non-exercise activity when fed more. Researchers deliberately overfed a random sample of 16 healthy young adults for 8 weeks. They measured fat gain in kilograms and change in energy use in calories from activity other than deliberate exercise, so fidgeting, daily life, and the like. And there's the data again. We've seen this. So we used Minitab. Remember, that's a program that works for this stuff. And this is our sample, right? We don't know the population, which is typical. And then we have our residual plot. We also have a histogram of the residuals, so we can check all of this stuff. And this is what you're normally going to be getting for this data. You're going to be getting a printout. So we can construct and interpret a 90% confidence interval for the slope of the population regression line. So we're going to do a one sample, t interval, for slope. Okay, our conditions, we have the liner. So looking at our residual plot, we see no sort of pattern forming, so we know that this is a linear regression. Independent. Well, we could say that 16 healthy young adults is less than 10% of all healthy young adults. Normal, we want a normal distribution of residuals. Well, looking at this, it looks approximately normal. It doesn't seem to be a major skew or outliers. There's a little bit of skewness here, but it's not too bad. Equal variance. So we don't see any sort of fanning in or fanning out in this one, right? There's a little bit of fanning out maybe. As we get further along, it looks like things are farther away, but overall, nothing bad, right? These are close together, and then these are kind of farther apart as we go, but it's not that major, so it looks like there's some equal variance going on here. There's just this one up here. And then random sample, I think that was stated. Yep, random sample. So now we need our t. Well, all of this stuff is given to us in the table. So our t is negative 4.64. So when we form our interval, we have our b, plus or minus t star times the standard error of the slope. So note that the t is different than the t star. So we can use that t value where we can use our t distribution. For a 90% confidence interval, that means that there's 5% in each tail. So we go to Menu, Statistics, Distributions. We're going to do an inverse t with 0.05. And the degrees of freedom is n minus 2. We had 16 young adults, so that means we have 14 degrees of freedom. So negative 1.76. So our slope is negative 0.0034 plus or minus 1.76 times our standard error, which is 0.00074. Notice how our slope is right in the middle, and now we can interpret. We are 90% confident that the interval from 0.009 to 0.002 captures the true slope of non-exercise activity increase. So now we're going to run a t-test for the slope of a regression line, a test, not an interval. We use regression lines to relate to quantitative variables, right? We've been talking about that. What would the slope of a regression line be if there were not a relationship between the two variables? Well, if there was no relationship, the slope would be 0. Okay, or beta would be 0. So for a t-test for slope, we look for beta equals 0 or the alternatives, not equal to 0, greater than 0, or less than 0. So here's an example. A college teacher asked a random sample of 10 of the 250 students in her introductory stats class to record the total number of time and hours they spent studying for a particular test, and then combine these times with the students' scores on the test. She then performed a regression analysis on the data. Below is a numerical and graphical output from her computer software. So we have all the data. This is the scatter plot of the 10. And then we can check all the conditions and stuff. We're looking for the data providing convincing evidence that there is a linear relationship between time spent studying and test score. Okay, so, let's check the conditions first. So is it linear? Well, there's not really a pattern in our residual plot, so that works. Independent, 10 is less than 25, which is 10%. So our 10% condition's met. We want a normal residuals. These got kind of mixed up, but that's okay. It looks like our normal probability plot looks linear, so we have normal distribution of residuals, which is good. There's not really any fanning in or out. Everything looks like there's an equal variance, so that's good. And then we know that there is a random sample, I believe it said. Yep, random sample. So now we can do the procedure. We have a one sample t test for slope of studying and test scores. Oh, I never wrote my hypotheses. So the slope is 0 would mean that there's no relationship, and then we're looking for evidence against that that there is a relationship. It doesn't say greater than or less than. And then beta is our slope of the regression line relating time spent studying and test scores. Now, all the values, this means we need to find all of the stuff in this little table. So we know that our slope is 12, right? That's our statistic. Then we need our t, which is 4.25. We are given our p-value of 0.003, and then our degrees of freedom will be 8, right? Because our sample was size 10. So n minus 2. Well, that's it. There's no calculations here. Since 0.003 is less than 0.05, it usually will tell you what the level is. It didn't. It's okay. We reject the null and conclude there is a relationship between studying and test score. So studying really does help improve your test scores. Notice this relationship sounds a lot like chapter 11, the chi-squared. Well, this is for two quantitative variables. Chapter 11 was for two categorical variables.